Yesterday, I asked you to solve a problem. Okay, so Hatzel and Ringel prove that if you have a bipartite graph that is decomposable into even number of Hamilton cycles, then this graph is supermagic. So let me recall the definition. It is possible to assign numbers, distinct numbers from one up to the number of edges to this graph, such that when we will check the weight of a vertex, weight of a vertex is the sum of the numbers assigned to the incident edges, then these weights are the same for every vertex. And this is exactly, these examples are exactly what I ask you to do. Okay? So the existence is proved or it's guaranteed by this theorem. And I told you that I will show you how to do it. So let us consider a simple situation that we have a bipartite graph that that contains just two Hamiltonian cycles. We have the composition. Yesterday you found out that this problem it is possible to solve using magic square. So let's try to have a little bit bigger example. We have a graph on 10 vertices. Here we have two cycles. Yes, and now I will show you how you can find it. So first we will start with the first Hamilton cycle, and this is the way how we will label the vertices. Many of you find, maybe I should ask whether you have a solution. Somebody know how to do it? You have a solution. Okay. So congratulations. Yeah. So what we do, there are many ways how you can do it. So this is just one way. So we will label the edges of the first cycle like this. 1, 2, 3, 4, 5. And then we will go in the opposite direction. 6, 7, 8, 9, and 10. And we will check what are the weights. Yeah, here we have the weights. And what is interesting to see, we have one weight, 7. Then we have 4 vertices that have the same weight, 12. And then the other vertices have weight 11. And then we will use, or we will try to label the second cycle. We can do it in a similar way, or we can use this labeling scheme. So we use something that we call as a dual labeling. So look how I will get the labeling. Yes, so when you will check the corresponding edges, their sum is always the same. 20 plus 1 is 21. Yeah, so 2 plus 19 is 21. So we have a dual labeling, and this dual will guarantee us that we will have some nice properties. Something that was true for the first labeling will be also true for the second one. So it is not complicated to see that we have here again one extra vertex that is that has weight 35, and then we have two groups of people. So we see that if we will check the edge labeling is inducing a coloring. So we see that this graph is free colorable. And now we can just join these two cycles together. Here we can see, yes, that look, here we have vertex V1, we join into this vertex V4. Every even vertex has a green color. So it will be joined with a green vertex here. And check the sum of the green vertices. 31 plus 11 is 42. Blue one, 7 plus 35, the result is 42. And the red one, 12 plus 30 is 42. And of course, it is possible to extend this algorithm for bigger structures. And it is not necessary to join, if not, of course, not for this case, the small case, but if you have a bigger structure, we can also obtain a different graph, not just our original one. Yes, so we say like we have circular graph that we join every second vertex and then every fourth. So we can do it in this way. So labeling of cycles in this way it's easy. The result presented by Nora Hatzel and Gerhard Ringel, it's only for bipartite graph. But something similar, it is possible to do also when we have decomposition into odd number of cycles, into odd cycles. Of course, for small cases, you will be not able to join the corresponding edges because then you will have parallel edges. But if you have a bigger structure, then you have more freedom how to connect the vertices, and you can do it in such. So this is the solution for this one. Okay, any questions or is it clear? Okay, so we will continue. Today I will speak about Antimagic graphs. I will give some definitions of graph labelings. So I will introduce you what everything cover the problem of graph labeling, and I will introduce you several variations on Antimagic labeling. Okay, so we will consider only simple graphs. And what is graph labeling? So graph labeling is any assignment that sends numbers. Usually we send positive integers, but if we do not restrict on positive integers to the vertices, edges, or faces of a graph or their combination. Okay, so when we label only vertices in a graph, we call such labeling vertex labeling. When we label only edges in a graph, such labelings are called edge labeling. So magic labeling is type of edge labeling. Then when we label vertices and edges of a graph, such labelings are called total. Of course, when we label also faces, so we have more combinations. Yes, so we have a plain graph and we can label vertices, edges, and faces, or just faces in a graph, or edges and faces. So we can see that we have many possibilities. Yeah? So this is how we just label. Of course, we can repeat numbers or we can use distinct numbers. So you can see that there are plenty of possibilities. And now, how we can label. So usually what we identify with the labeling is the weight. And again, you can find many different definitions. Sometimes the weight is sum of some elements, sometimes it's different, sometimes it's product. So you have plenty of graph labelings. So, and we can, of course, we can check what is the weight of a vertex, weight of edge, weight of face, or we can check some structures, like we will check some subgraphs in our graph, and we will check the weight of the corresponding subgraph. We will check every subgraph, and we will check every weight. Yeah, and in my case, I will only consider the situation that when we have the labeled graph, we will check the corresponding weights. There are two extremal cases. Yeah, one is that all weights are the same. Such a case, we speak about magic type of labeling. The other extremal case is then the set of all weights consists of distinct numbers. In such a case, we speak about anti-magic type of labeling, or it is called irregular if we allow that the numbers can repeat. Okay, so here you can see many of variations. Okay, so let me briefly explain these notions: vertex weight, edge weight, and face weight. So consider that we have a vertex V, and then weight of a vertex V, when we label only edges of a graph, is what? Yeah? So is the sum of the labels of edges that are incident to this vertex. Yeah, it's easy to see. When we have total labeling means that we label vertices and edges in a graph. And then what is the weight of a vertex V? The labels of the edges that have one endpoint is vertex plus the vertex label itself. And of course, when we have vertex labeling, then the weight of this vertex is the sum of the labels that are assigned to the vertices at distance 1. But you can find labeling that they will check not distance 1, but vertices at distance 2 or some distance, say D. Yeah? And you have variations because you can include this vertex. In such a case, we speak about inclusive labeling, or you can exclude it. And in such a case, we speak about non-inclusive labeling. Okay, so very many variations. Okay, what is the edge weight? If you have a graph and you will check one edge and you would like to know what is the weight of this edge. Again, it depends on the fact what we label in the graph. If we label only vertices in a graph, then the weight of the edge is defined as the sum of the labels of its ends. Yeah. When we label vertices and edges, we call such labeling total labeling. Then the weight of an edge is the sum of the vertices and edge. Is it clear? So you always, when you read some paper, you need to start with the definition. You need to know which type of labeling you are studying. So this is very important. And what about phase labeling? Yeah, if you have a plane graph, it makes sense to consider some planes, some phases, and then again, what does it mean? Let me explain this notation. First index, these indices are either zeros or ones. 0 means that the corresponding elements are not labeled. 1 means that we label, and it is in the order. First, vertices, edges, faces. So 0, 1, 0 means that we do not label vertices, we label edges. We do not label faces. Yeah. So how many combinations we have? It is easy to see that 0, 0, 0 has no sign because we label nothing. Yeah. So how many other combinations we have? 7, 6, 7. Yeah. Yeah. 2 cubed minus 1. Yeah. So here in this example, it means that we label only. Yeah. Do you need more time for? Would you like to ask something? Okay, so when we label only edges of a graph, then trivially, what is the weight of the face? Yeah, only we check the face, and we check the edges on the boundary of this face, and the weight of this face will be the sum of the labels that are assigned to the edges that are on the boundary of this face. Yeah, it's natural definition. We have here second example. We have labeling of type 1, 1, 0. What does it mean? 1 for the vertices, so we label vertices. 1, the second index is 1. It means that we label edges. And 0 for faces, so it means that we do not label faces. And then, what is the weight of the face? We check the face, we check the boundary, and we will sum all the corresponding elements that are there. Yeah, so vertices and edges. And we have one more example when we have face weight under the labeling of type 1, 1, 1. So vertices, edges, and faces are labeled. In this case, the weight of the face is the sum of the label of the vertices, edges that are on the boundary of that face, and the label of the face. So what do you think? How many different labelings we have? Thousands. Okay, and if you like it, there is always space for you to start somewhere and to find some results. Okay. Now let us consider this problem. So yesterday we were dealing with a problem. Assign numbers to the edges of a graph such that when we will check the weight of every vertex, they are the same. And now the problem is different. Now we require that we again assign numbers from one to the number of edges. To every edge we assign distinct numbers, but now we require that the weights of all vertices are distinct. Yeah. So this will be now our problem. Let me explain this notation, what is mentioned here. VAE, vertex, antimagic, edge. Edge labeling means that we label only edges of the graph. Vertex antimagic means that we check the weights of the vertices, and they must be antimagic, they must be distinct. Okay, so many times such shortcuts are used. So here we have a formal definition. This kind of labeling is known as antimagic labeling. So what we do? We try to assign numbers from one up to the number of edges to the edges of a graph, and we will check the weights of vertices. Here is the definition how the weight of a vertex is defined. And all the set of the vertex must consist of distinct numbers. Here it has no sense to be called for this problem. The definition was defined for numbers from 1 up to number of edges. So starting from 1. Of course, it has sense to start with some other number. For regular graphs, yes, for regular graph it will be the same, but there are usually, it's some from the historical reason that they start just from 1. Yeah. And again, it is possible to find, I will explain. Okay, so somehow when you have a graph and you don't restrict on labeling from starting from 1 consecutive numbers, you just say use distinct numbers. Maybe you have feeling that it is possible to do if you don't restrict on consecutive numbers. So this is a really big restriction. And what do you think? If we have a graph, okay, so this definition was defined by Hatzel and Ringel, and this is a very small example. Please try to do it. Okay, try to find Antimagic labeling of this graph. So how many edges we have here? 8. So try to find Antimagic labeling for this graph. Yeah, just to have feeling. Yeah, because it is good when you try to do it. Yeah. Something like that. You can try. There are many. Okay. Because what I would like to do it separately and then compare with your friends. Yes. So assignment, I have one solution, but you will see that you will try to do it and you will be able to do it very quickly. Yes. Just like the terminology, like to be consistent with the other one. You will see. You will see what will happen. Yeah. This is not big graph. So yeah, try, do it just randomly. And maybe you will be happy and you will do it on the first time. Almost any way. Yes. Yes, that's what I would like to tell you, to show you, yes. But it's just, this is about feeling, trying, yes, try, and you will see. Then you will be maybe more, then you will believe me that what I present you, it's true. Yes. Do you have some? Yeah. Was it easy? Yeah. Do you have the same labelings when you compare? You need more time, or I can show you the solution. Just for feeling, try to do it. Yeah, this is first time that for many of you, this is first time that you see this type of labeling, and try whether it is possible to find such a labeling. Try first one, and you will see whether it will work. Yeah. You have some? Okay, so maybe we can check this one. This is my solution. We can check the weights. They are distinct. Compare it to yours. You have the same, but maybe you have the same. Yeah, but maybe somebody else has different. Yeah. So you can see that finding anti-magic labelings for a given graph, it's quite easy. And not only that, if you compare, you can find many different anti-magic labelings, yeah, for a given graph. So your question is whether not to start with some other number or to use non-consecutive integers, yeah, because this is more challenging. Another question is, what do you think? If you have arbitrary graph, is it possible to find such a labeling? Do you have feeling? Probably yes. Yes. There is a very famous anti-magic conjecture by Hatzel and Ringel, and they conjecture that every connected graph other than K2 is anti-magic. My first question, why K2 is not anti-magic? Why K2 is the only exception, trivially. We have just one edge, so the both vertices they must have the same weight. Yes, you said number one. And now we have so nice conjecture, but for conjecture, what we need to prove it. When you will be able to do it, you will be very famous. So, but maybe somebody of you will prove it, okay? And Hatzel and Riegel, they conjecture a weaker conjecture for trees. They conjecture that every tree, of course, except K2, is antimagic. But nobody proved it. No, nobody. Yes. And you know, you tried, and it was easy. Yeah. If you have a graph, you can find such a labeling in general, but you know, for a given graph, you can find many distinct labelings, but in general, to prove it, it's very complicated. Of course, there are known a lot of results for some special classes of graphs, regular graph, or you know, something like that. But to prove it in general, it's very complicated. There are some results, like if you have a graph with sufficiently large minimum degree, then it's antimagic or something like that. But in general, it is still open. Okay. Sorry. 1996. I don't know. Yeah. So we had this situation, yes, that if you have a graph, you can find. So you can draw a graph with 2022 vertices, yes, and you will find it quite, you know, it just needs time, but you will be able to do it. But in general, to prove it is complicated. And now the question is what we can do now. So if we are not able to prove something, we try to give some extra condition for that, and maybe we will prove something similar to that. Okay, so what we will do? We will follow somehow the historical way how it was solved. So Bodengeg and Walter, they gave a restriction on vertex weight. Yes? So when we have antimagic labeling, we require just that the weights of vertices are all different. And now, what we have? Our problem is the following. We have a graph, and we assign again numbers to the distinct numbers to the edges of the graph, starting from 1. Numbers. And now we will check the weights of the vertices. And what we require that the set of the weights forms arithmetic sequence. And so we have additional property. Arithmetic sequence is difference D. Yeah, this is the meaning of this parameter, and A is the smallest, the first term in this arithmetic sequence. Okay. So here we have a formal definition. Yeah. An AD vertex antimagic edge labeling, the shortcut is BAE, AD, is an edge labeling, is bijection from the edge set to the set of numbers from 1 up to the number of edges, such that when we will check the weights of the vertices, they will form arithmetic sequence. Yes, so the weights are A plus D, A plus 2D, and so on. And the last one is A plus number of vertices minus 1 half one. Okay, we have this graph. Yeah, so you can try to do it, or I can show you. Okay. Sorry? No, it's there are, you know, the question is for which D is you can get for a given class of graphs, for which D is you can find the result. Yeah, you will find the range for D. Yes, when we put D equals to 0, then we have magic type of labeling. Yeah. Maybe I will show you the solution, and I will ask you to find labeling for simpler case. Okay, this one. This is solution. I will. I need one more vertex. Yes, we have cycle on odd number of vertices. Try to find, you can start with a smaller cycle, C5. Yeah. Try to find labeling of this cycle such that the weights are not only distinct, but they are maybe consecutive, then the difference will be 1 or some other difference. You have the solution. Somehow it is similarly to this case. Yeah. So try to label every second edge. Yeah, so what we get? 1, 2, 3, 4, 5. And then 6, 7, 8, 9. And we will check the weights of the vertices. So what we have? 6, 7, 8, 9, 10, 11, 12, 13, 14. It's very nice labeling. It has very nice structure. It's very known. It's we use it many times. And now, what we will do? Is it possible to give here some extra edges such that we will obtain a 4-regular graph, and the result, and for the resulting graph, we will again obtain labeling with difference 1. We will use numbers. Here we use numbers from 1 up to 9. So the next numbers are 10, 11 up to 18. And how we can find the labeling? The trick is the following. Look. So we have, there will be edge outgoing from this vertex, and it will go somewhere. Yeah. For every vertex, we can have this situation. So the end vertex is somewhere inside. So it is independent of the structure. And now, look, what we will do. We will, you know what to do? We will, here we have the vertex with the smallest partial weight. And here we will assign the maximal number. So what we will get? Plus 18. So the partial weight will be 24. Here for this vertex, the outgoing edge, we will assign 17. Yes, so the sum of the partial weight plus the outgoing edge is again 24. Do it for the others. Yes, so 16. Again, we have partial weight 24. 15, 14, 24, 13, 24, 12, 24, 11. Oh, okay. It's metrical advantage. 11, 34, 10, 24. And now it doesn't matter how we will join, because some of these edges will go to this vertex, also to this one. So it doesn't matter how we will join it, and how we see that the resulting labeling will be antimagic with difference 1. Because then the resulting weight will be what? 24 plus the label of some ingoing edge. But as these edges are labeled with consecutive numbers, so we have that the resulting total weights are also consecutive numbers. And this trick is used many times. And it's really nice, yes, to see somehow we fix some partial weight, and then we close it somehow. So it doesn't matter whether we will make a regular structure or you will do it in any way. And you need to get for a regular graph. So this nice construction will allow you to find many Antimagic labelings or Antimagic labelings for different classes of graphs. Regular. This trick works only for odd cycles. Okay. Any questions? Okay. So we can use this type of labeling for finding the labeling for K5. Any questions? Do you need more explanation? Okay. Okay. So we know that there is one way what we can do. We can ask for the weights that form arithmetic sequence. Another way, what we can do is it's not really restriction, we can extend the domain. So we will not label only the edges of a graph, we have a total labeling, we label also the vertices of the graph. So the problem is the following. Find a total labeling for given graph such that the vertex weights are distinct. Okay? So this is the problem. This type of labeling is called vertex antimagic total labeling. Let me explain. It's hidden here. Total labeling, it means that we label vertices and edges in the graph. Vertex antimagic means that we check the weights of the vertices, antimagic, that they must be distinct. Okay? And this labeling was defined by Martin Bacha, Bertol, McDougall, Mirka Miller, Rinovia, Simanjuntak, she will come next week, and Slamin. Okay, so this is the problem. You can try. Okay. Here we have two examples. So here we have vertex antimagic total labeling of paths on 5 vertices. Yes, we assign numbers to edges and vertices of a graph, and we will check the weights of the vertices. Yes, for example, for this vertex, it is 6 plus 3. For this vertex, it is 7 plus 3 plus 1, 11. Yeah, we have something like that. Then we have another example, vertex antimagic total labeling of cycle on 9 vertices. Is it clear what we have? Okay. And now there is a very nice result proved by Mirka Miller, Udem Panelsi, and Joe Ryan that all graphs are vertex antimagic total. For any graph, you can find such labeling. Okay? And now I would like to show you the algorithm how to find it. Okay, so at the beginning we have an arbitrary graph, and the result will be vertex antimagic total labeling of the graph. So maybe somebody wants to come and do it. Would somebody wants to come? We have a graph, this one, for example, or we can choose any. Okay, it has 7 vertices, 8 edges, and we try. I will show you algorithm how to find such labeling. It's a really nice algorithm. I like it really. Would you like to do it alone, or somebody is so brave that come? Sorry. I will tell you how to do it if you would like. I will show you the steps. Would you like to try? Okay, so what we have to do. So we have 7 vertices, 8 edges. So it means that we use numbers from 1 up to 15 to label vertices and edges in this graph. Okay. And now, for the first step, choose any numbers. It is up to you. And label in an arbitrary way the edges of this graph. Any numbers. For example, you like that. But you can do it as you like. just use distinct numbers for labeling edges. Okay? So the first step is assign arbitrary number to the edges of the graph. It's up to you which numbers you use. Then what we will do? We will check the partial vertex weights. Yes. So what is the partial weights? It's the weights under the edge labeling. Yes. So what we have? The weight of this vertex will be, the partial weight will be 16. Yes. For this one 5. Yes. So we know how to do it. We check the partial weights. It's not a problem that some of them are the same. Okay? But we know that the set of partial weights form non-decreasing sequence. And now there is a trick. Now we will label the vertices of the graph. We use the non-used numbers. So here, my non-used numbers are numbers from 9. Yeah, but if you decide to use different numbers, you will use your unused numbers. So in my case, I assign numbers 9, 10, 11, 12, and so on to the vertices of this graph. And how I will do it? I will assign the smallest number to the vertex with the smallest partial weight. Of course, I have several possibilities, yes? 10 is to the second smallest, and so on. So I have non-decreasing sequence, increasing sequence. And you see what we get as the result when we give it together. Yeah, we assign numbers, and then we will check the weights, total weights. So what is the weight, for example, for this vertex? Yeah, it's 16. Where is the smallest one? 14. It's not. Yeah, here I have highlighted the total weights. Yes, the total weights is a sum of the partial weights plus the label of the vertex. Yeah, so this is really nice algorithm. I really like it. I will speak more later about it because it is possible to modify it and to get the results for other cases. Yes. So here, let me repeat. We would like to get vertex antimagic total labeling. The weights of vertices must be distinct. So we start with labeling of edges. We assign numbers to the edges of the graph in arbitrary way. We will check the weights, the partial weights. They form non-decreasing sequence. And then we assign labels to the vertices of the graph. And we have two sequences, we have two functions. One is non-decreasing, the second one is increasing. So together we get increasing function. Any question? Is it clear how it works? Okay. So here is the algorithm. You can see here the formal way how to do it. Yes, so first step, label the edges with any integers from this set. Then we will denote the vertices such that the weight, the partial weight of the vertices will form non-decreasing sequence. And then we label the vertices with the not-used integers such that the weight of the, if we have the vertices with the smaller weight, we receive smaller. Okay, and the resulting labeling is a labeling, vertex antimagic total labeling. Yeah. Okay. The beauty of this algorithm is also in the fact that this algorithm will allow you to do many different labelings. Okay, so let me explain what does it mean, super. Super in this case means that we use the smallest numbers for labeling vertices. It's easy to find such labeling because we will keep the smallest vertices for labeling vertices and we will start with the larger numbers for edge. Yeah. Reduce, it means that it is that the vertices are labeled with the largest numbers. Yeah, so it's a reverse number, reverse weight. Yeah. And we can also find many labelings that are neither super nor reverse. Okay. So many different labelings we can get. Okay. And now we know that every graph is vertex antimagic total. So we can ask whether it is possible to get some more, to give some more conditions for such a labeling. Yeah, so what we can get, we can require that find such a total labeling of a given graph that the resulting vertex weights are not only distinct, but they will form some arithmetic sequence. Again, the smallest weight will be A and the difference will be B. So this is a definition of AD vertex Antimagic total labeling. And again, question is, for the given graphs, for which D such labeling exists. And sometimes some authors also study the case for which A we can find it. But for me, it's if I can find some labeling for given D, that's fine. Yeah, there are no some bounds for D. And now, consider the cycle. Yeah? Start with odd cycle and try to find such a labeling, vertex Antimagic total labelings with some difference D for a cycle. What we get? Look, forget for a while for these edges. And so what we have this scheme for labeling of one cycle. We get a difference when we have a partial result for labeling only edges. I can write it again, maybe for smaller example. One, two, three, 4, 5, 6, 7. What are the partial vertex weights? 5, 6, 7, 8, 9, 10, 11. And what we will do, we just need to complete the labeling to add labels to the vertices of this graph. How we can do it? To get the resulting labeling with some nice arithmetic sequence for the weights. What we can do? It's easy. Can we get a difference? Can we get difference 2? How we will get difference 2? Yeah. And so we will continue, yes. So here we have the partial weights for arithmetic sequence with difference 1. And what we can do? We can label the vertices such that we here to the smallest vertex we will get the 8. Yes, 8. Here 9, 10, 11, 12, 13, 14. So we have two arithmetic sequence, both with difference 1. So the resulting sequence has difference 2. Can we get other difference from this one? Can we get difference 0? Yes. We will label the vertices in opposite direction. Okay? So we will start 14, 13, 12, and so on. And so then the resulting difference will be 0. And the question is, can we get the difference 1? This is your task. Try to. Yes. So now try to assign labels to the vertices of the graph such that the resulting labeling will have difference 1. For this one, for odd, in general, for odd cycle.
But using this initial.
Yes. For a while you forget on the. It is not important to check the labels of the edges. You just work with the weights of the vertices. Partial weights. So we have partial weights. 5, 6, 7, 8, 9, 10, 11. Yes. So to these partial weights, we somehow would like to add some numbers, consecutive numbers. Yes, starting from 8. But if you don't want to work with big numbers, you can start with 1. Because you will just decrease every label by 7. Yeah. So somehow, yeah, distribute these numbers. Again, it's a very nice trick that is many times used. You can try to do it if you would like. Maybe I will give you time, yeah, because you know, it is good to know how to do it. And many times I forgot how to do it, so I play with just these numbers, and then you will find the solution. I will tell you I forgot how to do it, so you have to show me. Or I will give you more time and you can try to do it, and then you will tell me, okay? This is really nice, you know, the way how to play with the odd numbers. Okay, we have, yes, we have odd cycle and we play like that. Maybe you can work during the coffee break. You will tell me the solution. Okay, it's not complicated. You can try to do it. Or you can try to find the solution just for 5 numbers. Yeah, for some smaller sequence, and then you will see how it works. So would you like to continue on dealing with this problem, or can we continue with something new? It will be some nice way. Yeah? So just find the way how you do it. Labels every second. You have a solution? Maybe I will give you time, and during the coffee break, you will know the solution. Yeah. Sometimes we feel happy when we find solutions, so why not to, you know, to give you this possibility to be happy. Okay. So, here we have 2 examples. Would you like to solve this, or we can continue? Please tell me. Continue. You have solution? It's not complicated. Yeah, but it's unnecessary calculations you get. So we have a solution. Yes. Yes, every second. Yes, and you can also write the resulting waves. Yes. So this is the way how we can do it. Thank you. Thank you. Okay. So you will, when you will try, you will try. Okay. So now we know that every graph is vertex antimagic total. So come back to this algorithm that was presented by Mirka Miller, and Joe Ryan. And it is possible, why this algorithm is also very nice, is that it is possible to modify this algorithm for also for other problems. Okay, so when we have a problem, this one, find a total labeling of a graph such that now the edge weights are distinct. So what we will do, we will have a graph. We will assign again numbers to the vertices and edges of a graph, but now we will check the weights of the edges. Yes. So we have to do this one. This type of labeling is called edge antimagic total labeling. Again, total labeling means that we label vertices and edges of a graph. Edge antimagic means that we edge. It means that we check the weights of edges. Antimagic, it means that the set of edge weights must consist of distinct numbers. And they prove that every graph is edge antimagic total. This is nothing else, just the modification of their labeling for vertex antimagic total. And how we will do it? How we can do it? Yes, the problem is, yes, so you can explain. Yeah. First, what we label first? We would like, look, it's easy to, if you understand the logic of the original algorithm, it is easy to modify it for this case, yes? What we have, edge antimagic total. We would like to fix the weights of edges. So it means that we start with labeling of which elements? Vertices. So we assign numbers to the vertices of the graph in arbitrary way. Then we will check the partial edge weights. It doesn't matter that they are not distinct. Yes, they form non-decreasing sequence. And we will fix the edge weights by the labeling of edges. Yes? So it is the beauty of this algorithm is that it is possible to apply it also. And so I would like to stop for a while here. So when you will read some papers, it is not just, when you read result in a paper, you will see, oh, that's true. But it is very important also go through the proofs when you are reading some papers. Because in the proof, you will find many interesting things and some hints how to solve other problems. Okay, so from a result is fine, but don't skip the proof. In the proof, you will find inspiration for other problems, for how to solve them. Okay, so we have this one. And now I will show you how it is possible to modify this labeling for labeling of plane graphs. Okay, so here we have a formal definition of labeling of type ABC. We know what is it. Yes, A, B, and C are numbered either zeros or ones. We assign the first A is for vertices, B is for edges, C is for faces of a plane graph. And if there is, on the position is 1, it means that we label the corresponding elements. If there is 0, it means that we do not label. Yes? So we have this, here is the formal definition of labeling of type ABC. And again, we have many variations. What we can check? We can check the weight of the vertices. We can check what is the weight of edges or weights, or what are the weights of faces. And we require that these weights are distinct. And the question is, for how many, in which cases, we can find such a labeling or prove the existence of antimagic labeling of the given type using the results of Mirka Miller, and Joe Ryan. Okay, so trivially, they prove that every graph is super vertex antimagic total and edge antimagic total. Okay, So how we can reward these results using ABC terminology? How we can do it? So what is vertex Antimagic total labeling using ABC terminology? How we can reward it? Every what? Every skip this super, but you can keep it. Yes, is but vertex Antimagic total. So ABC. This means just for what we label in a graph. So when we have a total labeling is labeling of type 1, 1, 0. Yes. So we have a labeling of 1, 1, 0. And we check the weights of the vertices. But we have to consider plane graphs, of course, because otherwise it has no sense. Yes. So we have immediately from this result, we have that every plane graph is vertex Antimagic total of type 1, 1, 0. And the second one, that every plane graph is H Antimagic of type 1, 1, 0. And just by modification of the algorithm, we can prove these results. Of course, not everything is covered by this, but we can, for example, we have that the first one, every plane graph is space Antimagic of type 1, 1, 1. Okay. And now my question is, not visible, that how we can modify the algorithm represented to you for this case. So choose one and tell me how we will find such a label. For example, how we can prove or obtain space Antimagic labeling of type 1, 1, 1, arbitrary plane graph. How we can find such a label. You know? Yes, we would like to fix some property for phase weights. So that's why at the beginning, we do not label the phase. Start with labeling of vertices and edges. And we do it in arbitrary way. We check the partial phase weights under this vertex edge labeling. And then, according to this partial phase weights, we label the faces. And so the trick is like this. Okay, I'm not sure that I have a time. Yeah. So maybe I will stop here. So thank you for your attention.